It's my pleasure to introduce Roman Ludwig today. Roman did his studies, he's from Stuttgart and he did his studies in University of Tübingen. He studied physics. After a theoretical astrophysics group physics master's in Tübingen, he came to University of Zurich Hospital to work with Jan on medical physics problem. And he started in 2019, so that's the second year. And today I think he will talk about their recent work on lymphatic cancer progression. So with that, I will leave it to you, Roman. Thank you very much.
Exactly. Thanks a lot for the invitation and giving me the chance to speak here. I'm going to present what we, wait a second. Oh, sorry. What we were working on in my first year, which is a probabilistic model for lymphatic cancer progression. So first, a bit of the clinical background of this work. Here you see a slice through the head and neck region, and in green you see those see the lymph vessels, and in those bean-shaped bubbles are the lymph nodes. And now a patient might present with a primary tumor in the oropharynx, which is here, the back of your throat, basically, and some visibly enlarged metastases that you can see on MRI or PET-CT scans. And now the clinician, of course, that treats this patient with radiation oncology would irradiate the primary tumor, and of course everything that looks suspicious, like these enlarged metastases. But regions further down the lymphatic chain, like here in the orange circle, there it's not so clear should you irradiate or not, because there's a fair chance that there are microscopic tumor cells present, and not irradiating this region would therefore compromise tumor control. But on the other hand, if there is nothing present and you irradiate unnecessarily, you introduce harmful side effects, like especially in the head and neck region, this really reduces your quality of life. It can introduce difficulty of swallowing and dryness of mouth and whatnot. So yeah, to assess this, basically this risk of harboring microscopic metastases somewhere in the lymphatic network of the head and neck region, we set out to develop a model that predicts this risk. And for that, we first looked at those regions. These are called lymph node levels, anatomically defined regions in the head and neck, which are necessary because not every person has the exact same number of lymph nodes in the exact same positions. So surgeons have defined these lymph node levels and enumerated them for both sides of the neck with Roman numerals from 1 down to, I think, at least 10. And together with our clinician, Panos Badampas, we then try to connect these lymph node levels in a way that represents the flow of the lymph liquid. So we did this like that, and this is basically the starting point, the abstraction that we did for this model. Then, of course, each of those lymph node levels is then associated with the diagnose, which is the mentioned MRI or PET-CT scan. Could also be a fine needle aspiration or a palpation if you just feel for enlarged lymph nodes. And if you take away now the head, you're left with this this network of binary random variables. So we have here the hidden true involvement of the lymph node levels that we want to predict, and we have associated with, for each lymph node level, the respective observation, the diagnosis from one of the diagnostic modalities. And of course, you have the primary tumor, which is always there and always involved. Then you can parameterize this model with the probability of involvement due to the primary tumor. So what is the probability that the primary tumor spreads to one of those lymph node levels directly? So that's basically the lymph liquid that is present in every cell drains through the lymphatic system directly into one of those lymph node levels. Then you have the spread probabilities among the lymph node levels. So that basically, given that a lymph node level is involved, that it harbors already microscopic metastases, these parameters give the probability that it spreads further down in the lymphatic network or the lymphatic chain. Now, this does not necessarily need to be a chain like this. There could be other connections, and I'll get to that later. But for the first step, we model it like this. And then, of course, you have the sensitivity and specificity of the used diagnostic modality, which is predetermined by whatever modality you use. We can now write down all the probabilities that we need to compute, let's say, a likelihood for involvement or a risk. We start with the observation and the diagnosis, which is pretty straightforward. So given a state, a true hidden state of one of the lymph node levels, you can compute the probability for observing it to be healthy or metastatic. And this is just basically given by the sensitivity and specificity parameters. And similarly, you can compute a probability for metastatic involvement in one of the lymph node levels, given the metastatic involvement in its parent nodes. And this is then a combination of those parameters B and T. So combinations of the probabilities that the tumor spreads and the lymph node levels itself. And what I just described is basically the Bayesian network model that a postdoc and my colleague in our group worked on up until 2019, and where my work started. So this Bayesian network model works really well, and it's very intuitive, and every parameter can be interpreted very well. However, the problem is that as this is a sort of a developing system, so a tumor grows, and as time and T stage of the tumor progress, you would also expect that the risk for microscopic involvement in the lymph node levels increases. And that's a bit harder to capture in a pure Bayesian network. So we wanted to extend the network and use some model that has an explicit notion of time steps. And to do that, let's first reduce the network a bit, look at a simpler example here, and put aside the diagnosis for a second. And also, since the tumor is always there, it's basically not really a random variable as it's depicted here. It's just a fixed parameter that connects to each lymph node level. And then you can basically say that at the next time step, we model the involvement of the lymph node levels as dependent on the state before. So now, for example, lymph node level 3 doesn't get it directly from up there, but from one time step previously. Parameters stay the same, and these horizontal connections, they are basically just there to prevent self-healing, so that if a lymph node level is already involved, it cannot become healthy again. And in that way, you can construct your chain from a time 0 to a diagnosis time TD, where the patient comes to the hospital and gets diagnosed. So in total, we now know that the patient starts healthy. He must have been at some point. And then after some number of time steps, he comes in because maybe he has symptoms, or he goes to a health checkup and gets diagnosed with cancer by chance. And treatment starts usually timely afterwards, so that we cannot continue to model the progression of his disease in such a way. So so this, you could say this is a hidden Markov model or a dynamic Bayesian network, I think is also a term that would apply here. And there exist very powerful inference algorithms for those types of models. However, they usually all assume that you have a series of observations, so that for each time step you have a diagnosis and not just one in the end. And also, they usually assume that you know how many time steps your problem or your system evolves over. Well, we do not know that. We do not know TD. And those are two problems that we need to tackle, and that's what I'm going to talk about now. So first, let's group the involvement in the lymph node levels, so them being cancerous or not, into a state that covers both of them. So state 1 is both are healthy, state 2 is one is healthy, one involved, and so on. Where the final state, the state that can't evolve anymore, is the state where all lymph node levels harbor metastases. And then we can, using the probabilities I described earlier, we can compute the probability to transition from a state at time t to another state at time t+1, which is given by this product here. And here in the theta, again, comprises the parameters b and t. And then you can express this in a matrix where for each state at time t, you transition to another state at t+1, and the probability is then given by this sort of lookup table. I guess if you know hidden Markov models, that's nothing new to you. And similarly, you can do the same thing for an observation matrix. So for each state that a patient could end up in, you have this lookup table. What is the probability of actually seeing a certain diagnosis given that state? Which is again just a collection of terms with the sensitivity and specificity. So,
sorry, Roman.
yes.
Will it be possible for you to discuss the basic model a bit more, the basic Markov model? Because yeah, I don't know. For me, it's a bit difficult. I don't recall anymore, and then maybe it's difficult for me to follow the rest afterwards. So,
I think I will get into a bit more detail.
Okay.
Maybe I just wait 3 or 4 slides more.
Yeah.
And I think it will become clearer.
Okay.
I hope, but if not, just interrupt me again, and I'll go back. That's no problem.
Okay, perfect. Thank you.
So now that I've introduced those 2 matrices, we have the starting state. So basically, that's a vector that says I'm in the healthy state with probability 1. All other states have probability 0. Then we have this transition matrix that is basically where our parameters live in, and the observation matrix made up of sensitivity and specificity. And that's all we need. That's a hidden Markov model is defined by those 3 objects. And if you just multiply them together, the first multiplication will give you the probability to end up after 1 time step in any other state based on the starting state. And if you multiply that then further with this observation matrix B, this will then give you the probability to observe, give you a vector with the probabilities to observe any state given that you started in a healthy state and iterated over 1 time step. Does that make sense now? Or should I go back?
Can we go back maybe?
Yeah, sure.
Shortly.
Okay. So basically, so we have this kind of model. All of those are binary random variables. And we know that they are in state 0 at the beginning at t=0. And then we have those parameters b, which are represented by this little dot here, and the parameters t, which are represented by those diagonal lines. So, and at each time step, there's a probability that the primary tumor spreads his cancer cells into this lymph node level or this lymph node level, and therefore that one of those 2 or both become involved. Once they are involved, which can only happen after 1 time step, right? They themselves can spread to other lymph node levels. So in this example, level 3 cannot spread anywhere. It can just stay involved if it is involved, while level 2 could spread to level 3. So level 2, if it becomes involved at a t=1, then it could, with a certain probability, infect lymph node level 3 at t=2. And all those probabilities that you need to compute this transition from one state to the other, you have here. So for example, the probability of involvement of x n = 3, so this one, at time step t+1, for example, time step 2, given the parent node. So this would be lymph node level 2 at time step t, and these parameters that can be computed very easily. You can just write down a table for that.
So this is a Bernoulli distribution, isn't it? So each random variable is a binary
Exactly. Yeah.
random variable.
Yeah.
So this is essentially the distribution is given by one scale, is parameterized by one scalar.
So it's actually more. So in this case, for level 3, it would be B3, because at every time step you could have an involvement from the tumor, or it could receive cancerous spread from the tumor, and you could receive spread from a parent lymph node that's also involved.
Right. So there are two scalar parameters then.
In this case, yeah. But if you have more parents, we would have more. Right?
Yeah. For each parent, there is one parameter.
Yeah,
right?
exactly.
Yeah, perfect. Yeah, thanks.
Cool. Yeah, thanks for asking. That's maybe clarified it for others as well. And yeah, exactly. So the product of these terms over all the lymph nodes or lymph node levels would give you then the complete transition probability from one state, which is a collection of the involvement of both of them, from T to T+1. This you can then collect in this transition matrix. Here you see some examples. So for example, the probability to transition from a state where lymph node level 2 is involved and lymph node level 3 is healthy to the state where also lymph node level 3 is involved would be given by B3, the probability that primary tumor spreads, plus T2 to 3, so this one, minus that both spread, probability that both spread. Yeah. Okay, and then this is just sensitivity, specificity. And then you multiply them together and you get the probability for a certain diagnose or for all diagnoses after you evolve the system from one time step. You can then just put in another transition matrix to compute the probabilities to see any possible diagnosed D after 2 time steps, right? And the nice thing about this is already marginalized over the patterns of progression. So we don't need to know or infer which lymph node level was involved first. So when the patient comes in and he has both lymph node levels involved, we do not know and we cannot know which of them was involved first. We can of course guess that lymph node level 2 was probably involved first, but we're not sure. So this elegant marginalization comes in handy for us. And then generally, you just take this transition matrix to the power of t, and now you need to know the number of time steps. And sadly, we also cannot know that, so we need to marginalize over that as well, and introduce a conditional probability distribution that basically says, okay, let me look at this in detail. So these are 2 examples for such probability distributions, so such time priors, we call them. So let's say you involve the system over 10 time steps, or you evolve it over up to 10 time steps. Then these distributions give you the probability that you diagnose a patient at the respective time step. So for example, if this is the distribution over the time steps, then the probability to diagnose a patient after 4 time steps would be given by this 25%. And then you can imagine that someone who comes in with an early T stage, so with a small tumor that has not yet spread into bones or other tissue, that's a patient who goes regularly to health checkups. Therefore, his condition has been diagnosed earlier than someone who comes in with a large tumor that has already infiltrated adjacent tissue, who might be a person that is reluctant to go to the doctor even though he or she has some symptoms. So therefore, the probability of diagnosis for those 2 different kinds of patients is spread apart. And then basically the idea is that for every time step, so we evolve the system for 0, 1, 2, 3, up to 10 time steps, and compute the risk of involvement. And then we weigh it with the respective value in the time prior to get a marginalized risk for each state, which we then multiply with the observation matrix. Is this clear? Are there questions regarding this? All right, perfect. So I just noticed an error on this one. So of course, this is the risk for each state marginalized over time, and then you need to multiply that with the observation matrix. So here you should have an orange vector for the risk of diagnoses. What we then do is we multiply this with a data matrix that indicates all the patients in our database. So, for example, if we have 17 patients that presented upon diagnosis with no nodal involvement, then we have a column here that says we had a patient that has no involvement. So this is the healthy state, and all the other states we're not interested in. And this respective entry in the vector back here is then 17. So we have 17 patients that have no nodal involvement. While on the other hand, we had 6 patients where we're not sure if it was this state or this state. So why would we not be sure? That could be because we only diagnose. So for example, if you use fine needle aspiration, so you puncture one of the lymph nodes with a needle, extract some material, and look at it on a microscope, then you would only see that. Then you would only basically diagnose one lymph node or one lymph node level. And if you then see that this one lymph node was healthy or involved, then you only know that about this one lymph node. You don't know about any others. So, and this is characterized by a column that has multiple entries. So in this case, this would, for example, mean that we do know that at least one lymph node level was involved. In this case, lymph node level 3. And so we marginalize over all states that have an involvement in lymph node level 3. So yeah, basically our data is represented in those two objects, this matrix and this vector. And if you compute that, you get the likelihood of observing a certain data set given your parameters. And the data set we used is a table of patients. So you have rows of patients with reported lymph node level involvement, which was reconstructed from frequency reports in a clinical paper, which consisted of 103 patients that had a neck dissection. So we had a full pathology report on each lymph node level of each patient. They all had squamous cell carcinoma in the oropharynx. That's the region I showed on the first slide in the neck. They all were early T stage, so relatively young tumors, kind of, and they were previously untreated. And then we used Markov chain Monte Carlo sampling to sample those parameters, those B and T probabilities from the likelihood I just explained. We used an uninformative prior, so nothing special going on here. And you could then use this set of parameters to compute whatever you're interested in. For example, the risk. So you can just compute the probability of a state given a certain diagnose and given a subset of your sample parameters to compute an estimator, not the risk itself, but an estimator for the risk. And we performed this sampling, and we got this result. It's not super clear what you see here. Basically, we have 4 lymph node levels. Therefore, we have 4 probabilities that the tumor spreads to the respective lymph node level, and we have 3 probabilities that they spread among themselves. And this is plotted here in this corner plot. which consists of 2D and 1D marginals of this sampled probability space. And with that, you can then compute what we actually want to do, what we set out to do. You can compute the risk of involvement. So for example, if you're interested in the risk of involvement in lymph node level 2, this one here, given a certain diagnosis. So let's say a patient comes in and he doesn't present with any suspiciously looking lymph node levels. So there's no involvement. Then you can compute that you have about a 25% chance of having microscopic metastases despite a negative diagnosis. However, if you see enlarged or suspiciously looking lymph node levels, lymph nodes in lymph node level 2 and 3, then that will almost guarantee you that you will have, that you are metastatic. The probability jumps up to 90%. And yeah, similarly for level 3. So if you observe metastases in lymph node level 2, that significantly increases your risk for metastases in lymph node level 3. Yeah, also I want to mention here, so the green and reddish histograms, those are the results from this hidden Markov model that I just explained. The blue histograms, those lines here, are the results sampled from the Bayesian network model. And the orange line is a maximum likelihood estimation from my colleague, whose paper I showed you earlier. So this basically shows that given that we don't differentiate T stages, the predictive power of the hidden Markov model is at least as good as the one of the Bayesian network. So that's sort of a validation that the principle works. And you can also see this here. We did a threefold.
Sorry, yeah. Can I ask a question about the previous slide? So here, for example, in the second, the second diagram that covers the whole row,
yeah,
we're looking at the probability of metastasis in level 2, right?
Exactly, yeah.
And the 4 different plots are conditional probabilities depending on what is given, right?
Exactly, what is given as a diagnosis.
So in the third one, it's like the probability of metastases in level 2 given metastases in level 2. What is that? Like the third histogram in the second.
This one?
Yeah, exactly. This third one.
Yeah.
What does this represent?
It's the probability of microscopic metastases in lymph node level 2, given that you observe something on imaging in lymph node level 2. Did you observe metastases or enlarged
should this
lymph
not
nodes?
Be 1?
No, not quite, because the sensitivity and specificity of this diagnostic modality that you provide is not 1, right? So you could have a false positive, basically.
And your model knows about this because you trained it
exactly,
with some data like this.
Yeah.
Yes. So actually, for the third one, it's even if you observe it, like in the plot below,
yeah,
the purple, even if you observe it, you're only 40% sure that it actually exists.
Exactly. Yeah. What I might have to add here is that, so sensitivity and specificity from this data set, we set this to 1 for training, right? Because this is pathology data. So someone looked at the microscopic level. Someone sliced those lymph nodes that he extracted during the neck dissections, sliced them up and looked on those slices on the microscope. So we assumed, although that's probably not quite true, we assumed those reports here to be the ground truth. And then if you come in and have a patient and diagnose him with an imaging modality where sensitivity and specificity are certainly not 1, probably closer to 0.8 or something. That's why the model says I'm more certain that this is a false positive, because I have seen the ground truth in 147 patients, basically. And also it's actually very rare that you only have lymph node level 3 involved, because that is one of those levels that usually gets its metastases from afferent lymphatic spread from lymph node level 2. So if you have only a suspiciously looking metastasis lymph node in lymph node level 3, then there's a fair chance that this is just because maybe you have a cold and your lymph node is enlarged. Yeah, exactly. Great.
But so maybe just to understand the sort of the clinical application, maybe I can just say that the cases that the situation we are most interested in from a practical application is the cases where, you know, the observation is negative, right? Which would be like these 2 histograms to the left, you know, where either no observed lymph node metastasis or only in level 3. And then we are interested in the probability. Okay, well, what is the, given that we don't see anything suspicious on the image, what is the probability that there is truly tumor anyways, right?
Yeah.
So from a practical perspective, this would be the relevant situation.
This way around is more interesting because clinically, if you see something suspicious, you would usually just to be sure, you would irradiate it. While the other way around, when you see nothing, you're more interested in, might there still be something? Yeah, I think I'm not going to talk about this too much. Just some validation. Now back to this one here. So let's say you have again the computed, or back up a bit. Sorry, I'm a bit. So why we were doing all of this was basically to be able to incorporate T-stage into our model. But sadly, we don't have a data set that incorporates T-stage. So we only have this one reconstructed data set. And for some reason, clinicians that collect this kind of data, so head and neck cancer specialists, they don't report the raw data set. They just report on statistics of their data. So we have no data to train our model with that includes T-stage for a given patient. So what we did to show that our model works in principle and can extend to other T-stages is that we took that data set that we have and put it into our model. And then we added another data set where we basically only fix the ratio of N0 patients, meaning patients that have no lymph nodes metastatic, to N+ patients, so patients that have some form of involvement. And this ratio, this is given in the literature. You can find this to be, for example, 25% for late T-stage and 35% in early T-stage. And yeah, so basically we do this using this data matrix that I explained earlier, where this is the healthy state, this represents the healthy state, and this marginalizes over all states that have some nodal involvement. And then we fix our time prior, which is a binomial distribution for the early T stage, for example, to be 0.4. So that's the binomial distribution for n equals 10, and the p value to be 0.4. And we include the late T stage prior, or the parameter of the late T stage prior. We include that in the sampling process, in the learning, and allow the model to spread those two probability distributions apart to match this target of N0 to N+ ratio. And then we can go in again and say, okay, what's the risk for involvement in lymph node level 3, given that we see only suspiciously looking metastases in lymph node level 2. And now we can differentiate between early T stage and late T stage based on this learning. So here you see the blue histograms are early T stage. One is when you see no involvement anywhere. This blue one shows the risk of involvement for early T stage when you see suspiciously looking lymph nodes in level 2. And then the orange one is the same thing, but for late T stage. And as you would expect, you have the least amount, the smallest risk for early T stage when you have no bad diagnose. And you have the highest risk for late T stage when you already observe metastases in the adjacent lymph node level. So this was kind of to show that in principle, the methodology works. Sadly, we have no real way to validate this as of now. But yeah. So are there questions regarding the model here? Or regarding these findings? Then I would go on to what we're planning to do or what we're doing right now. So all that I showed you up to now, we wrote a paper about that, which got luckily accepted just last week. And as soon as it's publicly available, I'll also share it with you. I think I shared a preprint with you already. And now I'll briefly talk about what we're doing now and what we want to do next. So far, the model just covers the side where actually the tumor is, so the ipsilateral side, but we would like to extend this to the contralateral side, so the other side of the neck where the tumor isn't. And we hope that this works fairly straightforward because we assume the symmetry of the neck, so those transition probabilities among the lymph node levels should be the same on both sides, so the blue arrows should be symmetric, while due to the lateralization of the tumor, those red arrows or the associated probabilities might differ. And then we also want to extend this to more complex networks that include more lymph node levels, which have a more intricate connections among them. And what we were doing over the last maybe 9 months to a year was also to collect the data set at our hospital at the USZ. So mostly one of the clinicians there took the effort to report the detailed patterns of involvement of 287 patients that had squamous cell carcinoma of the oropharynx, and that will be published soon along with an interface to explore that data set interactively. And we hope that this motivates clinicians to publish their raw data as well, and to share that with us so that we can improve our model. So concluding, I think we've developed an intuitive and physically motivated model where the structure is, has an explicit notion of time and is interpretable in terms of its parameters. It's also computationally rather efficient. You can still do learning on a normal laptop. But we need clinicians and institutions to publish more of their raw data instead of just statistics based on them to improve our model and do some validation, some actual validation. Yeah, finally, we have published our code along with the paper that will be published soon. And with that, I thank you for your attention. And are there questions?
That was very nice. Thank you, Roman. Are there any questions in the group? Maybe I can start actually with not the question about what you've done, but what you're going to do. So your model kind of gives these probabilities for the lymph nodes for being infiltrated. Do you think it would make sense to now take those probabilities and based on them look at the images again and try to see that if, perhaps with this more refined suspicion, we might be able to see something in the CT image?
That is actually a great idea. So because what we noticed in this data set we collected already is that, so this is an imaging data set, so there's no pathology reports in there. And we noticed that the ratio of, for example, involvement in lymph node level 2 is very high. And we think that this is because the clinicians expect lymph node level 2 to be irradiated anyways in the case of oropharyngeal head and neck cancer. So they are not fully objective in their diagnosis. They just say, okay, even though I don't really see something that is clearly a metastasis here, it will get irradiated anyways, so I can just contour it. And if we use sort of our model to look at the data again, at the images again, that might give us a more objective look at these images. Yeah.
So they would delineate it just because they think that, well, in most of the cases, it's already in.
It's a bit of an assumption on our side.
Okay.
But what we noticed, so in this data set, we have multiple modalities. For example, we have, for many patients, we have PET and MRI, also CT often. And if you just compare, if you compare them and you assume that they must have come from the same true distribution of states, right? So you can write down all your states, all the, for example, if you have 4 lymph node levels, you have 16 possible states where a patient could be in. And there's some true but unknown distribution over those 16 states. And then you look at the 2 histograms that you get when you look at the diagnosis from MRI and from PET, and you try to make sense of that. That doesn't work. So it can't be just sensitivity and specificity that determine those 2 distributions. There is some sort of bias in this data set. And we think it could be, and our clinician also thinks that that's a possibility, that you would delineate or mark them as positive in part because you think that will get irradiated anyways.
Thank you. Any other questions?
Can I ask one?
Sure.
So I think a little bit in continuation of this. So how sensitive is the model to this D matrix, this diagnosis matrix, like this specificity and sensitivity values? Does your inference results change much when this changes?
Yes, of course. So first, if you only have imaging data, you will, you basically destroy information, right? When you have limited sensitivity and specificity. So you will never get the same precision. And to get anywhere near the same precision or accuracy, when you do the learning compared to the pathology data set, you need much more data. So for sensitivities and specificities around 80%, you probably need 5 to 10 times more data compared to pathology reports.
I see. I guess I meant more like, so now you set this value to 80%. Am I correct? Or
yes, we took, yeah.
And where does this number come from?
That number basically comes from estimates of sensitivity and specificity.
Okay, so you compare like the reports based on imaging to reports based on really ground truth data, and there you see 80%.
Yeah. So in those plots that I showed, so in this case we learned, so we trained the model with pathology data where we set sensitivity and specificity to 1, yeah. But then we used literature values for I think a PET CT scan, which were around, I think you have been more than 80% for the specificity and a bit less than 80% for the sensitivity, and then produce those risk estimates using those values. So, and if you set, for example, the sensitivity and specificity to 1, then those would all collapse to single points, right? Those,
yeah. I see, but because in your training you actually have like very high sensitivity and specificity, the model you learn is actually a correct model, so to say. So yeah. You don't suffer from it. I see. Thank you. Yeah.
if there are no other questions, I think I'd like to thank Roman again.
Thanks a lot for having me.
Very much.